All right, now we're going to talk about an application of factoring, which is something from section 12.1 of Lehman's book. And I'm going to do this in one big video, so it won't be 5 minutes long, so it'll be continuing on through 5 minutes. So first of all, what we have to do is we have to explain what a rational expression is. So remember that a rational number was a quotient of two integers, while a rational expression is a quotient of two polynomials. So we express polynomials with capital letters. So we say some p divided by some q. See, it looks like a rational number even. And the q can't be 0, and p and q are both going to be polynomials. That's what a rational expression is. So rational expressions can be monomials divided by monomials, binomials divided by monomials, polynomials by polynomials, etc. So we are going to talk about the fundamental principle or fundamental theorem of rational expressions. And this is just like the fundamental theorem of fractions. We have a polynomial over a polynomial, a rational expression, and if we multiply both the numerator and the denominator by another polynomial, q and r can't both be 0, or can't be 0, right? Then it's going to be equivalent to our original rational expression. Now, of course, this works with division as well, since our multiplication is the same as division. So we use this with fractions using the fundamental theorem of fractions before, and this is how we did it, right? We had 15 over 35, and we found the prime factorization or of the fraction 15/35. Now we had a GCF method too, but that's not what we want to apply. We want to apply our prime factorization method, because that's what factoring actually is. Factoring a polynomial is finding its prime factorization. So here we go. Prime factors of 15, 3 times 5, and prime factors of 35, 7 times 5. And then we use canceling, right? To cancel the 5 with cancel the 5, and we're left with 1 and 1 here. So multiplying out, 3 times 1 is 3, and 3 times 7 is 7. And so there's our simplified expression or fraction. And we're going to do the exact same thing with polynomials. We're going to use the fundamental theorem of rational expressions, or the fundamental principle of rational expressions, to simplify a rational expression. So we're going to start with a really, really simple, easy rational expression. So it looks more like a fraction than a rational expression, because it is a monomial over a monomial, it is actually a rational expression. So on this, we would have that same idea, right? Now with the numbers, because they're numbers and we do know how to take out GCFs, we can go ahead and cancel those out, right? Out of each of these, we can take a 5, so that leaves us a 3 here, and out of the 35, that leaves us with a 7 here. But remember, that's the same example I just did above. And then this is quotients, right? X to the first over x to the first. That's our quotient rule, 1 minus 1, which is 0. Or another way of looking at it, they cancel, don't they? And so in the numerator, I'm left with a 3y, and the denominator, I'm left with a 7. And that is simplifying a rational expression. Now let's look at a few that are a little bit more complicated, and we're going to be applying the skills that we just learned in factoring. So we're going to look at the numerator here, and we're going to say, can we factor that? Now the rational expressions, finding the restrictions on a rational expression, that is finding out where the denominator is equal to 0. And I'll talk about that a little bit later. So we have finding if this one factors. Well, x squared doesn't factor. We just leave it as a monomial. So I'll rewrite it as x squared. And then the denominator, I'm going to see a binomial here. The only thing I have to attack so far is a GCF. So I see that these each have an x in common. So I'm going to take that x out. And from the first term, I'm left with an x, plus from the second term, I'm left with a 2. Now, because this is a product, right, it's products that we can factor, and that's why we want to factor, so we can cancel. So 2 minus 1, or one of these cancels with one of those, leaving us with an x in the numerator and an x plus 2 in the denominator. Now, one of the things that I want you to be really, really careful of is the fact that there is no canceling in addition. So a lot of times, I'm going to write this in blue, a lot of times students will see this term here and this term here, and they'll go, oh, I can cancel them out, and they'll cancel this one and cancel this one. But this term is a part of a sum, and you can't do a canceling in a sum. So let me show you this. So if I have 2 over 2 plus 7, that's kind of exactly what I have right here, right? There, 2, that's a term, and x squared, that's the term. Those are the same terms, plus something different, whatever it happens to be, right? So, would you tell me that you could cancel that 2 and that 2 and get the same answer as if you added these together and then did that? Your answer would be no, right? There is no canceling in addition. That fraction bar comes first, and so we have to simplify the numerator, then simplify the denominator, and then we can see if we could simplify that further. It's going to be the same exact thing in fractions. We can't do this. We can't cancel here and here and have this, and then say that that is going to be equal to 2/9, which is what it should be equal to. So canceling in addition is not allowed. So over here what we want to say is no way, right? There's no way to cancel. So don't make that mistake in rational expressions either. All right, now moving on to our next problem, we want to take a look at the numerator, take a look at the denominator, and simplify by factoring. So numerator, we have a 3 in common, so I'm going to write in 3 as a GCF, and then take 3 out, I'm left with x, minus take 3 out, I'm left with 2. Now in the denominator, my leading coefficient's negative. Remember, I don't like that. So I'm going to take out a negative, and I'm going to take out a negative 4. And then I'm going to be left with a positive 2x. Oops, not positive 2x, sorry, just positive x. And then I'm going to take a negative out of a positive, and that leaves me with a negative. And now here is where I'm left with 2. And so now I can see that there's an x minus 2 in common with each of these. And so my final answer is just going to look like a negative fraction of a negative 3/4. And remember, the negative can come out here because remember that whether I have a negative fraction or a negative numerator divided by a positive denominator, or a positive denominator divided by a negative denominator, they're all exactly the same. All right, moving on to my next examples. We have a little bit more complicated, but still the same idea. We're factoring. So in the numerator, I have to factor by grouping because what I see is 4 terms. So from these first 2 terms, I'm going to take out an x, and that leaves me with an x plus 2. From the second 2 terms, I'm going to take out a negative because they're both negative, right? So I'm going to take out a negative 3, which will leave me with a positive x and a positive 2. And then from those 2 terms, I have the binomial GCF of x plus 2, and then that will leave me with an x minus 3. And then the denominator, what I want to see is that they have a 4 in common. So 4, and then an x minus 3. And the x minus 3's, we're going to see are going to cancel. So 4 and x minus 3. And those cancel, and that's going to leave me with x plus 2 over 4. And again, don't get carried away. There's no canceling in addition, so that 2 and that 4 can't cancel and simplify at all. Our last one here, we have 20x plus 15. So we have in common here and here of 5. So I'll take that out, which leaves me with a 4x plus 3. And then down in the denominator, I have a 10 in common. So I'm going to take the 10 out, and that's going to leave me with 4x plus 3. Now I can cancel because I have a multiplication problem. So the 4x plus 3's will cancel, and I have a common factor here. 5 divided by 5 is 1, and 10 divided by 5 is 2. So my answer simplifies all the way down to 1/2. That doesn't happen very often, but every once in a while it does. All right, now let me just briefly talk about what the first set of the instructions set up here about finding restrictions. Restrictions on a domain mean that we can't have the denominator equal to 0. So in 35x in the denominator here, the x can't be equal to 0. That's called a restriction on the domain. Here in x squared plus 2x, that one we have to factor it first so that we can see it looks like x times x plus 2, and then we can say that, well, neither x equaling 0 or x plus 2 equaling 0 will work, because you guys know that anything times 0 is going to be 0, right? So that's a times b equals 0. And if a times b must equal 0, then either a could equal 0 or b could equal 0 to make that happen. So this is our a, that's our b. Either one equaling 0 makes it happen. So x can't equal 0 here, or just solving this here, saying that x can't be equal to -2. And that is called restrictions on the domain. So restrictions are finding out what values would have to be put in order to make the denominator 0. So what values make the denominator 0? And that is called a restriction. Now we'll cover that again later on, but that's exactly what it is. I just wanted to mention that. All right, that wraps up this venture into Chapter 12.